And we're live.
So lesson 3, law of conservation of energy. I wrote this. First of all, some terminology. In general, a force in the direction of the motion, like force 1 below, does positive work. A force opposite to motion does negative work. What I'm going to try and do today, Emma, is explain to you what I mean by positive work and negative work. I want to put that into some kind of a context. A little note, though, although work can be positive or negative, it is not a vector. It has no direction. It is a scalar. Right? So, what does negative work mean? We have to go off on a little tangent. I have to talk about energy. Energy is the ability to do work. And there are many types of energy. For example, there is the energy of motion. We call this kinetic energy. Any object that's moving has the ability to do work. So if I've had enough of Anthony's smarmy attitude and I decided to throw this at him, and it hit him in the face. When it hit him in the face, could it apply a force over a distance? Could it do work? Okay? Anything that's moving has kinetic energy. Anything that's moving has the ability to do work. In fact, to bring it to a stop, Anthony's face would have to absorb that kinetic energy. It would do work on his face, and he would say, owie. Heat created by friction. Heat is another form of energy. Gravitational potential energy. So, if I've had enough of Anthony's smarmy attitude, right now, can this lead weight, if I were to drop it, and it hit Anthony's head, would it do work? As a matter of fact, if I were to drop it, its gravitational potential energy would turn into the energy of motion, which is what? What have we called it? Ready? Does it have more potential energy or less potential energy now? It gained more. Where did the energy come from? From me. That's why I'm tired. Okay? We're going to start to talk about how you transform energy from one type to another, and you're going to start to realize that energy always has to come from somewhere. You can't make it up out of nothing. So gravitational potential energy, this is energy due to an object's position. Really due to its height. Higher it is, the more gravitational potential energy it has. Meteors that strike the Earth generally aren't all that large, but they're coming from a long ways away, a big height. They have an awful lot of gravitational potential energy. Oh, and then it turns into kinetic. And when it hits the Earth, they come to a stop. The energy's got to go somewhere. It goes into destroying the Earth. Ask the dinosaurs. So potential energy is stored energy. So this first example of stored energy I called gravitational potential energy because that lead weight was just sitting there. Ignore the fact that my hands were trembling. That lead weight was just sitting there. Doesn't have kinetic. It's stored energy. There's all sorts of types of potential stored energy. Chemical potential energy. Gunpowder or food. The reason you eat food is it stores potential energy in the form of chemicals, and your body then turns those into the ability to do work. Other forms include sound energy. Sound is a form of energy. Elastic energy, example, the energy stored in a rubber band. Nuclear energy, the energy stored within the nucleus of the atom. Light is a form of energy. There's all sorts, lots and lots and lots of different types. Pause for a second. In this course, we're going to look at what we call
mechanical energy, which is broken down into two main types: kinetic and potential. Kinetic, the energy of motion. And potential, stored energy. Stored energy. And this lets me explain negative work. When you do negative work on an object, what that really means is that object is losing energy. It's giving its energy to something else. Electrical energy is stored in a battery. When you put that battery into some kind of a device, it's losing energy. It's doing negative work. Okay. Let's start with gravitational potential energy. This is the work that you must do against gravity in order to change an object's height. As an equation, we've already derived it. We said that work equals force times distance. When you lift something, which force are you doing work against? Which is written how? What's its equation on the Earth? Don't go cosmic on me. Sorry? mg. And I said a vertical distance we call h. This is the equation for potential energy. Gravitational potential energy, but I don't put a little g there. I get kind of sloppy. You want to know how much energy you've given an object? It's the mass times 9.8 times the height, which, by the way, is why, Anthony, that made you so much more nervous, having that lead thing over your head than this. Same height, same 9.8. What changed? The mass. Yeah, the mass. Okay? That's why we fire cannonballs and not little BBs. Even though they may travel at the same speed, one does way more damage. This one is on your formula sheet. You'll probably end up memorizing this because we're going to be using it again and again and again and again and again. You don't have to, but you probably will. So, Spencer has a mass of, turn the page, 75.4 kilograms. First of all, what's his weight? It's not 75.4 kilograms. Weight is a force. What's weight measured in? How could I find what have I called weight? Yeah, I don't want to use W for weight because that's work. We've called it the force of gravity. It's going to be mg, so it's going to be 75.4 times 9.8. I'll go 739. And it's a force, newtons. So when Spencer jumps, he can raise his center of mass 75 centimeters from the ground. At the top, how much potential energy does he possess? Okay. Potential energy is mgh. It's 75.4 times 9.8. Am I going to put 75 in for the height? What's the height? 75 centimeters, so what am I going to put here? Okay. How much energy will he have at the top? You get 554.2 units, energy, joules. Okay. Where'd that energy come from? His leg muscles, and the energy in his leg muscles came from his food. That's why when you don't eat properly, you feel tired. You can't do as much work. He did work, a force times distance. He did work to get to that height. He increased his potential energy. This is also why, by the way, it's more tiring to go upstairs than downstairs. When you go upstairs, you're increasing your potential energy. Where is that energy coming from? You. When you go downstairs, you're decreasing your potential energy. In fact, you could go downstairs doing no work by rolling or falling down the stairs. It would just hurt. The only thing you're doing, Manny, is just when you go downstairs, is you're just preventing yourself from injuring yourself, but you're doing it way more casually than going up the stairs because it's not costing you energy. Kinetic energy. I said kinetic energy was the energy of what? Begin with letter M? Motion. You know something has kinetic energy if it's moving. If it's not moving, it has no kinetic energy. You guys right now have no kinetic energy. Actually, technically you do because the Earth is spinning and you're moving because of the Earth, but certainly relative to the room, you have no kinetic energy. The equation. There is a lovely derivation, but I'm just going to give you the equation. My abbreviation for kinetic energy is KE. My abbreviation for potential energy is PE. 2 capital letters. Technically, that's wrong. Technically, it's bad to use 2 letters. The reason I use those is, so technically I'm supposed to use that and then call it EK for kinetic or EP for potential. But in Physics 12, that is electric field. That's energy, and kids get them confused all the time. So I go with this. Kinetic energy is equal to a half mv squared. You want to know how much kinetic energy an object has? It's equal to 1/2 times its mass in kilograms times its speed squared. You'll notice I'm not putting a vector on velocity. It's speed. It's a scalar, which is going to be really nice. So I looked this up. A .357 Magnum bullet weighs 8.1 grams and travels at 490 meters per second. How much kinetic energy does it possess? Well, .5. What's the mass if it's 8.1 grams? What am I going to write here in kilograms? Point. How many zeros? See, I think that there is 81 grams, right? Because a kilogram is 1,000 grams. So that would also be a little wonky. 0.0081. And then 490. And the most common mistake, I don't know why, kids forget the squared. How much kinetic energy is that? I get 972 joules. Absorbing that in a small area, the size of a bullet, all at once is terminal. Your body cannot absorb 972 joules in a small area. It can if we spread it out, and that's all a bulletproof vest tries to do. The nice thing is, because energy is a scalar, direction doesn't matter, all a bulletproof vest does is it takes the kinetic energy coming in this way and it spreads it out over as wide an area as possible. And you might say, well, how does it take energy traveling this direction and spread it that direction? Energy is a scalar. Direction's irrelevant. It spreads it out over a larger area, and we're hoping what happens is you're still going to have to absorb that force times distance, but we're going to spread it over a bigger area, maybe lower the distance. You'll break a rib, as opposed to having the bullet go into you and puncture an organ. Okay? Race cars. They are designed in a car accident to almost shatter, to almost fly apart. That's deliberate. Why? Each little piece that goes with it takes with it some little bit of kinetic energy. That's a little less kinetic energy that the driver has to absorb. And you may say again, well, wait a minute, how can a piece going that way reduce the amount of energy that I got to absorb if I'm wiping out going this way? Energy is a scalar. It's one of the nice things about energy. So if you ever watch a car accident on racing, you're like, boy, that car just seemed to like totally come apart. That's on purpose. It's intentional. Every piece of energy that it takes with it, that's less that the driver has to absorb. It's good safety. Dane, in a loud, authoritative voice, even better than your "and we're live," I want you to read this heading. Go for it, Dane, my friend.
Law of conservation of energy.
Thunder should be flashing right now. Lightning should be flashing right now. You should hear a deep rumble in your belly. There should be a shiver going down your spine. If you asked me to list the top 2 or 3 most important laws of the universe, absolutely this would be on them. Okay? There should be a shiver. The law of conservation, energy. That's really what there should have been an echo. What is the law of conservation of energy? It says this: energy cannot be created or destroyed. It can only be transformed from one type to another. This means that if we are looking at a closed system, a system that has no outside sources of energy, no machines hooked up to it, no nuclear reactor hooked up to it, no outside source of energy, the total amount of energy at the start and the total amount of energy at the end must be the same. As an equation, we write it this way: the amount of kinetic energy at the beginning, initial, plus the amount of potential energy at the beginning, initial, has to equal the amount of kinetic energy at the end plus the amount of potential energy at the end. Has to. Or, if we really want to be more accurate, if we want to include friction, or if we include friction, kinetic initial plus potential initial equals kinetic final plus potential final plus heat. Whatever's missing must have gone into the heat dissipated with friction. The energy that we lost, that we no longer have, must have gone into friction. Technically, Trish, sound and friction, other dissipative forces, but I'm going to lump that all in together as heat. Okay? Show you what I mean. Skateboarding. A half pipe is a terrific example of a conservation of energy situation. So here we have the, ask me later. Here we have the energy skate park. I'm going to put a skateboarder on this half pipe. Now, I have friction turned off. If friction was turned on, gradually his height would reach a little bit less, a little bit less, a little bit less, a little bit less. But I've turned that off. We're in our magic physics world. And I'm going to show you on a bar graph. What do you notice about the total energy? The law of conservation of energy says energy is not created nor destroyed. It can only be transformed from one form to another. Can you see the two transformations going on here? Yeah? As a matter of fact, when do I have maximum kinetic energy? When am I traveling my fastest? At the bottom. Oh, and in a coincidence? No, not a coincidence. When do I have the least amount of potential energy? At the bottom. When will I have the most potential energy? At the top. When will I be traveling the slowest? In fact, when will I be traveling 0 for a split second? At the. This is the law of conservation of energy. Now, the other nice thing about the law of conservation of energy is it doesn't matter where I put the height of 0. You gonna let me do this? Track playground, maybe.
Here's my little track. Okay. I can let there be 0. If I want to, I can let that be 0. If I put the skateboarder on here, a little badly, Mr. Dueck. Let's put him on here a little better, right there. And even this bump here, the nice thing is, because energy is a scalar, it doesn't care about the path that you take. All it cares about is where your initial and where your final were. In fact, I could even make this a bit more bizarre. Let's do this. Let's add a little dip. No loops. We have to go a little more intense on the physics here. What I do want to add, though, is a little hill. So even that hill, in theory, you'll notice doesn't make a difference. Energy is a scalar. It doesn't care about that bump right there. All it cares about is what's the lowest you got, what's the highest you started at. There's my before and after. In other words, energy is the best to analyze a curvy path when there is a change in height and a change in speed. Energy is the conservation of energy is the best to analyze roller coasters and most other amusement park rides. Okay. Let's go back to the introduction. This time, I'm going to turn on friction. Can I turn on friction, Mr. Dueck? Friction. So right now I have friction off. Pause. Turn it on, and I'm just going to have a very small mu, a small coefficient of friction, because skateboards are pretty good. Again, let's go to our bar graph. Let's put it, how about right here? Okay. But now you'll notice I've got another type of energy, thermal energy, heat. What's our energy slowly being wasted or transformed into? Heat. And that's why I have less potential. And if I have less potential, because potential is mgh, m didn't change, g didn't change, what must change? H, I can't go as high. Oh, and if I can't go as high, I can't go as fast because it's not going to be transformed anymore. The law of conservation of energy. In fact, this little toy behind me that you've all wondered about, the law of conservation of energy. I said, look at the skateboard park in FET, I just did. Show the marble energy transfer device, I just did. Okay? Even something as simple when you bounce a basketball. Beautiful physics there. Maximum potential energy, you're adding a bit yourself, so it's not a closed system, but if you pull your hand away, it'll keep turning into kinetic when it hits the ground, back into potential, but you lose a tiny, tiny bit to friction. The ball actually heats up. Any of you that play racket sports, like squash or racquetball, if you open a brand new can of balls, you have to smack it a few times to get them warmer, and they will physically warm up. They don't play right for a while. New can of tennis ball, same idea. Half the potential, halfway there, half kinetic, all kinetic right there. It also works for a pendulum, which is a curvy path, which otherwise with vectors would be terribly difficult to analyze. Because right here you're going this way, but at the bottom you're going this way, and then you're going this way. Ugh! Can you imagine trying to figure out forces and directions? Which way's positive? Which way? Who cares? Energy is a scalar. The phrase I use in Physics 12 is this. Is there a change in height? Is there a change in speed? Is there a curvy path? This is a job for conservation of energy. I used a similar phrase. Hey, are there more than one force? This was a job for a free body diagram. Well, if we're analyzing this type of thing, curvy path, change in height, change in speed, definitely conservation of energy. Even without the curvy path, it may still be a job for conservation of energy. All right, example 3. A projectile is launched straight up into the air. If its initial velocity was 84.3 meters per second, how high does it go? And I wrote here, use energy. We could probably solve this using D and V and T and a half AT, all that, but we can also solve this using energy because Read the question. Is there a change in height? Yeah. Is there a change in speed? Yeah. There isn't a curvy path, it's straight up, but I think energy will still work. We can solve this by saying kinetic initial, potential initial equals kinetic final, potential final. What was the equation for kinetic energy? You have to go back and look, but I gave it to you. You'll also end up memorizing it, but it is on your formula sheet. But you'll get tired of looking it up. Kinetic energy. Kinetic energy. A half. Okay. We have a half. And I guess initial kinetic energy would be a half mv initial squared because your mass isn't changing. Plus, what was the equation for potential energy? And I guess initial would be mgh initial equals a half mv final squared plus mgh final. Are any of these, before I go further, are any of these 0? Let's see. Is my initial speed as I take off from the ground 0? Is my initial height as I take off from the ground 0? Oh, that's convenient. Is my final speed at the very, very top 0? Oh, that's convenient. Is my final height 0? No. You will find often you can cross stuff off before you go further. In fact, eventually most of you will probably cross it off already on the blue line. Ah, that's 0, that's 0. You'll write it out and cross it out. So what I really have is this. A half mv initial squared equals mgh final. Oh, ha! Do you notice something else? And this is a good thing because they didn't tell me it. What? About the mass. So, do I need the mass? Why? Look at the equations. What happens to the mass? Turns out there's a mass in everything. If I divide by m, gone. That's good because they didn't give me the mass. In fact, what are they asking me to find here? Oh, H final? Okay, see it? How would I get it by itself? Oh, really? So if I hear you, you're saying the final height is going to be VI squared divided by 2G. It's a half VI squared, but can instead of timesing by a half, can I put the 2 on the bottom next to the G because that looks prettier? Yeah. By the way, what you've really just done is you've shown that D equals VI squared over 2A when VF is 0. You've derived, I don't know if you remember at the very beginning of the year when I gave you the VF squared equals VI squared plus 2AD, I said this one's tricky to derive until we get to work and energy. It pops out of work and energy. It really does. You don't need to worry about that. Hey, let's crunch the numbers. The final height is going to be 84.3 squared all over 2 times 9.8. Mr. Dueck, isn't it negative 9.8? Energy, scalar or vector? Scalar! Tuh! Who needs that? How high will this go? You get 362.6 meters? 362.6. And I could have figured that out actually with kinematics stuff. I could have said, reading the question, VI is 84.3, VF equals 0, A equals negative 9.8, D equals question. I could have done all the stuff from a couple of units ago. But where energy is nice is for part B. You see, part B, I'm going to be able to figure out what friction did, which would be very, which would be very difficult otherwise. Part B said, if the projectile only reaches a height of 72 meters, how much work did air friction do? Okay. Is there a change in height? Yeah. Is there a change in speed? I'm thinking this is a job for conservation of energy, especially since they're talking about work and work done by friction, which is another energy concept. Yeah, only I have to tweak my conservation of energy equation. It's going to be kinetic initial plus potential initial equals kinetic final plus potential final. Are they talking about friction here, Kyle? Yes? Then I better say there must have been some heat energy. I don't think that formula is on your formula sheet. The first one definitely is. I don't think I also then rewrote it with the heat option. I'm going to expect you to clue in, Manny. Oh, if he's talking about friction, the numbers won't balance without me somehow saying we lost some energy to heat, like the skate park that we looked at. Hey, are any of these 0? Starting on the ground and coming to a I get a half mv initial squared equals mgh. Kinetic energy is a half mv squared, so kinetic energy initial is a half mv initial squared. Potential energy is mgh, so potential energy final, mgh final, plus heat. Does the mass cancel this time? No. Why doesn't the mass cancel this time? Is there an m in everything, including heat? No, so I can't cancel out the m, which means now I need to tell you the mass. Mr. Dick, why don't you include it in the question? I don't on purpose, to let you know that sometimes the mass won't cancel. Specifically, when there's heat, the mass won't cancel. However, when there's no heat or almost no friction, the mass cancels. That's going to impact you guys later on. So I'm going to say up here, assume m equals 5.0 kilograms. Reed, what's this question asking me to find, my friend? Where is, how much work, keep reading. The work done by friction. Where in my 3 things is the work done by friction? Heat. So, get the heat by itself. How would I get the heat by itself? Minus, most common mistake, and I don't know why kids divide by MGH. I haven't, this is one I have not figured out yet why, but they do, and Sally's smiling because she saw it even in physics 12, she saw some kids do it. And I still don't know why, because there's a plus sign there and it seems to me to be fairly obvious. I don't know. Anyways, heat is going to be a half mv initial squared, subtract the mgh over. And now it's plug and chug-ish. 0.5, 5, what was VI? 84.3 squared minus 5, 9.8. It only got to 72 meters instead of the expected 362.6 meters. I'm guessing we lost a lot of energy to heat. .5 times 5 times 84.3 squared minus 0.5 times 9.8 times 72. Yeah, we lost 17,400 joules of energy to heat. This is not I can tell you, not knowing what this object is, it's not very aerodynamic. Is that right? Nope, it's not right. I got a 0.5 there. How about a 5, Mr. Dueck? MGH. 17,240? Okay, I'm sorry, 14,240. I read it, thought it right, read it wrong. 14,200. Wow. Oh, now it's back. Okay. This is, but I can tell you, Kai, since initially if I was 100% efficient, I would have reached 362.6 meters. I only reached 72. This is not very aerodynamic. This is shaped like almost like a piece of paper or something like a parachute. This is terrible. Again, conservation of energy, very handy to analyze ski hills, which are changes in heights, changes in speed, and curvy paths. At location Z, a 72-kilogram skier is traveling at 18 meters per second. How high up the next slope, this is timely for the Winter Olympics, how high up the next slope can the skier reach? Ski jumping, by the way, terrific example of conservation of energy. You start off with a high gravitational potential energy, you want to turn it into kinetic, and then see how far you can glide, essentially, right? Is there a change in height? Is there a change in speed? Is there a curvy path? This is a job for conservation of energy. Do they want me to include heat, or do they want me to ignore heat? And how do you know? It says ignore friction. So, are any of these 0? Is your initial kinetic energy 0? What was kinetic energy? What was the equation? A half mv squared. Is your v 0 at location Z? I heard someone say yeah, I heard someone say no, so I think one of you is wrong. Not just that, if my speed was 0, how the heck would I be going up the next hill? Energy's got to come from somewhere. That's witchcraft and magic, right? So, not 0. What about my initial potential energy? MGH, am I on the ground? Right? What about my final kinetic energy? If I'm asking how high can I go, when I get to the top, how fast will I be traveling for a split second? I'm going to come to a stop for a split second. Oh, but at the top, how high will I be? 0? No, not unless I'm a really lousy skier. Focused here? It's like people looking out the window. It's called an attention span. You know what? This is going to look like this. A half m v initial squared equals m g h final. Okay. Oh! Now, I noticed they actually did give me the mass of the skier. Did they need to, though, technically? What this really means, by the way, this is what explains why little kids can ski next to grown-ups. Mass cancels. If that wasn't the case, anytime grown-ups and little kids were skiing next to each other, the grown-up would have to constantly be slowing down, adjusting, slowing down, adjusting, slowing down, adjusting. Now, it's true, mass only cancels when there's no friction. Hey, skis, is there very much friction? So the grown-up has to adjust a tiny bit, slightly, but not much. What are we trying to find? Oh, how would I get the h by itself? So it's going to be, the final height is going to be vi squared divided by g, and instead of writing a 1/2 on the front, Manny, are you okay? I'll just put a 2 in the bottom. That's the same as the 1/2. That looks nicer. Oh, okay. What was VI? 18? squared divided by 2 times 9.8. How high up the next hill will this person go? Did I give them a name? Nope. Mystery skier. How high up the next hill will they go? Sorry, say that again? 16.53 meters. Anybody else? Oh, I better check that. People are being lazy. 18 squared divided by 2 times 9.8. 16.53 meters. I'll take that. Roller coasters. How many of you have been on a roller coaster before? Okay, cool. A 245 kilogram roller coaster car travels as shown below. At point A, it's moving 12 meters per second. Gotcha. How fast will it be traveling when it gets to the bottom of the hill, point B? Okay. Is there a change in height? First of all, what are they asking me to find? How fast? Speed, final speed. Is there a change in height? Is there a change in speed? Is there a yucky, curvy path? You know what this is a job for, probably? Something that's a scalar. The law of conservation of energy. To try and solve this with vectors, I mean, you can see your path is changing all the... It could be done. You'd need calculus and it'd be yucky. Why bother? You know what? Let's go right... Well, we got room down there. Did I give you lots of room? Sure. Plus heat or not? No? How do you know? Oh, ignore friction. Okay. And I guess roller coasters are probably greased pretty good. They're not frictionless, but I imagine it's pretty close. I'm guessing they have a pretty small coefficient of friction. Where kinetic energy is a half mv initial squared, potential is mgh initial, a half mv final squared plus mgh final. Oh, you know what? Are any of these 0? Kinetic initial, kinetic final, or potential final? Potential final, we're ending up on the ground. Anything else? Nope. Oh, but I noticed something else. Do you see it? Do you see it? Do you see it? Darian, were you on a roller coaster before? Did you have to step onto a scale before you got onto the roller coaster so they could carefully calculate your mass and keep everything in equilibrium? You didn't? Jake, have you been on a roller coaster before? Did you have to step on a scale before you got onto the roller coaster so they had to... You know why? Why didn't you have to step on a scale? As long as it's nearly frictionless. In real life, it's nearly frictionless. Not quite, but close enough. Yeah, real life. Or putting it another way, this is why a skinny person can sit next to a fat person on a roller coaster and we're not concerned about will it make it up the next hill. Okay? Mass cancels. This is why an empty roller coaster car can make it through the roller coaster just fine, the same way as a full roller coaster car can. What are we trying to find? VF. VF. You guys with me okay? Yeah, good, shut up. VF. What's in front? I know it's a VF squared, which means eventually I'm going to square root. Not yet. What's right in front of the VF? A 1/2. I'm going to show you a good trick. I'm going to clear out that 1/2 as a fraction by timesing everything by 2. I'm going to go like this. Times by 2, times by 2, times by 2. Now, why is that? First of all, have I done anything illegal? No, because equation solving says you have to do the same thing to everything, which I have. But notice what happens here, Kyle. 2 times a half cancels, and 2 times a half cancels. The 2 in front of the GH doesn't cancel, but at least it's not a fraction. In fact, I get a new and improved equation. I get VI squared plus 2GH equals VF squared. Put your pencils down, look up. See what I just wrote? See it, see it, see it, see it, see it? Don't write this down. Remember I told you back when I gave you that equation that I wasn't going to prove it until we got to work at energy? Take a look. Isn't that exactly what I just wrote in the bottom corner? Except instead of acceleration, what do I have sitting where the A is? Gravity, which is 9.8 units. What? Meters. Oh, it is an accelerate. Oh, look at that. There. This is where that equation actually comes from. It's a really easy proof once I've done work in energy. It's a much longer proof without it. It pops out naturally. Okay, pick your pencils up. Oh, how would I get rid of a squared? I'm going to get this. The speed at the bottom is going to be the square root of VI. I've scrolled down. What was VI? 12 squared plus 2, 9.8. What was the initial height? 18? Okay, so if you're designing this roller coaster, how fast will your passengers be traveling when they get to the very, very bottom? I'm going to type everything inside the square root first, and then I'm going to go square root answer. I'm going to go 12 squared plus 2 times 9.8 times 18. Enter. Square root. And I get 22.3. Yes? Meters per second. Pause here. Your homework is the take-home.